Hello everyone and welcome to Chapter 4. Now that we've gotten through the vector material on Chapter 3, we're going to combine that with the kinematics topics that we discussed back in Chapter 2. And what I'm going to do right now is I'm just going to go ahead and list out the 5 kinematic equations that we derived back in Chapter 2. And then we'll take a look at these equations to see how we're going to update them for our vector notation. And so we have AT squared. Oops. That needs to be final. So all these equations should be in your notes back in Chapter 2 material. And then we have what I like to call our missing column. So these are the terms that are missing entirely from the equation. Alright, so we learned in Chapter 3 that certain values need to have directions associated with them. Certain values do not. Those that do not are called scalar quantities. Those that do require directions are called vectors. And of the 5 kinematic terms that we have here, 4 of them are vectors. And those being displacement, the velocities, and the acceleration. The only one that is not a vector is time. Time is scalar. Even though we do think of time as moving forward, time does not have a physical direction that is associated with it. And so that means that for all of our kinematic terms, technically these 4 should have some little arrow hats over the top. And as such, that would mean that we would have to go through all of our kinematic equations, and everywhere where there's a vector term, we would have to put the little arrow hat over those vectors. And then we would have to figure out, well, how do we take the knowledge that we gained about vectors, where they have magnitude and direction, or as I prefer, components. How do we take the components of a vector and use those to solve kinematic systems where an object may be moving in more than one direction at the same time? So the first thing that I want to do is I want to make an update to our list of equations here. Now that we're going to be working in 2 dimensions and 3 dimensions, we need to consider that every one of these vectors can have x and y components, and then in some future discussions we'll extend this to include things like 3 dimensions, but not today. We'll just limit ourselves to 2D for right now. But this means that the first term that we have here, displacement, I have that listed as delta x, and that's because the x-axis was the first axis that we started discussing. We were able to revise that for a vertical system. So we could just as easily have replaced delta x with delta y, and we could go back through all of these kinematic equations, and we could rewrite the delta x's as delta y's, and everything would be good. But now that we have both happening at the same time, if we were to displace in this direction, we would technically have, oops, it's not a very good line there. We would technically have x and y components of that displacement. And so I need a way of describing what this two-dimensional displacement vector is going to be. And that two-dimensional displacement vector, it will be the vector combination of our delta x and delta y components, but we've done enough with vector addition already to know that anytime we add two individual vectors together, we get a resultant, and so we're going to call this delta r, where r is the resultant of adding together the individual displacements in x, y, and eventually the z-axes. And so that's the update that we're going to make here. Delta r is going to stand in for the displacement for our kinematic expressions. And delta r, it could be a one-dimensional vector, it could be 2D, it could be 3D. It all depends on how many components we're going to have in our system. Likewise, our other vectors, v final, v initial, acceleration, those can be one-dimensional vectors, they can be 2D, they can be 3D. It all depends on how many components we're going to be dealing with. But I'm not going to rewrite v final, v initial, a. Those can just stand in as they are, but I am going to go through and update our kinematic equations so that they all have delta r for the displacement vector. And then I can plug in the value for delta r as needed, depending on what kind of a system I have, if it's 1D, 2D, 3D. But we have to get into the habit of listing these terms as vectors. And so let's just take a look at these vectors. We'll see what they would look like in our list. Now, our displacement vector delta r as a two-dimensional vector would have components in the x and y direction. There would be a displacement along the x-axis paired with a displacement in the y-axis. We could then combine those components using the Pythagorean theorem to get the magnitude of delta r, and then we could use those same two components to find the angle in the xy plane that our displacement vector needs to point. Likewise, our initial velocity vector could have x and y components associated with it. And those components could be put back together with the Pythagorean theorem to find the magnitude of the initial velocity vector, and then we could use those same components to find the angle. And so this pattern is going to carry through all the way down. Our final velocity vector could have x and y components. Our acceleration vector could have x and y components. The only thing that's not going to have components is time. Time is a scalar. But I'll just go ahead and put time right down here. That value is going to be shared between the x and the y directions, because as something moves through 2D space, it's going to be moving along the x-axis with the same amount of time as what we would move along the y-axis. So what I want to do now is just to help us understand better why we want to split all of these terms up into their vector components. Let's go back to the cliff. And we saw a couple of problems in Chapter 2 where we would drop a rock off of the edge of the cliff, use some kinematics, find out how long it takes to get to the ground, how fast it would be moving when it impacts the ground. So we'll try that again, except now we're going to roll the rock off of the cliff. We'll give it some initial velocity in the horizontal direction. We'll say 5 meters per second. And we'll say that the height of the cliff is 30 meters. And things I would like to know are how long is it going to take for the rock to reach the ground? What will the impact velocity be? And you'll notice I have that written as a vector. And since we're now working with a two-dimensional system, okay, the rock is going to follow this parabolic path here. So all the way down, it's got x and y components to its displacement. Since we're looking for the actual vector, I would also like to know what are the components of this vector, and then let's put them together to produce magnitude and angle. And so that angle of our final velocity vector, you'll notice it's got a little bit of an angle to it. It will have a magnitude as well, but if we can get the x and y components of that final velocity vector, so we will have a little bit of a x and y component for that final velocity vector. If I can find those two components, then finding the magnitude and the angle is pretty simple. The other thing I'd like to know is how far from the base of the cliff do we impact the ground. So measuring from the base of the cliff out to where the rock strikes the ground, how far is that? Okay, so here's what we're going to do. We have all of these kinematic equations from Chapter 2. They've been updated for vector notation. So every one of these terms essentially has two pieces to it, an x and a y component. But I don't want to cram everything into a single expression, because things could get a bit overwhelming. Instead of having come on, eraser, there we go. Instead of having one expression for a two-dimensional problem, what if we could have two expressions in one dimensions? In other words, I already know that I'm going to be moving through two-dimensional space with this rock. What if I were to set up independent axes for the x and the y direction and just treat each direction as a one-dimensional problem? Obviously we're moving through 2D space, but if I could solve for the kinematics of this moving object along the x-axis and then separately solve for the kinematics along the y-axis, I could later put all that information back together in two-dimensional form. In other words, if we set up a reference frame like such, so this goes back to our 10-step problem-solving process. After you have everything drawn out and labeled, now is the time to select your reference frame. Actually, if you don't mind, I'm going to change that. I would like my y-axis to point down. And the reason for that is because the vertical displacement is going to be down. Gravity as an acceleration, so acceleration in the y direction is down. My final velocity has a component in the y direction that is down. So everything about this rock in the y direction is pointing down. I might as well let that be the positive direction for my reference frame, and I can save myself a lot of effort with not having to incorporate a lot of minus signs. And then as far as the x-axis goes, my initial velocity is pointing to the right. My final velocity has a component that is pointing to the right. The displacement of the rock is to the right. And so that makes everything in the x direction also positive. All right, let's see what we have to work with now. These are the things that we're going to be solving for, but now I need to see what I have available to work with. And what I like to do with any kind of two-dimensional kinematics problem is make myself a table of all of the kinematic terms. And if I can come up with the necessary 3 pieces of information, then I can solve for the other 2 using the appropriate kinematic equations. So in the x direction, I will have components of initial and final velocities, acceleration, displacement, and time. Likewise, in the y direction, I will have components of the same vectors and time. Again, time is not a vector, but the amount of time that elapses as we move in the x direction has to be the same amount of time that elapses in the y direction. And that's kind of important, because if these 2 values are the same, then that is the connecting aspect of this problem. So maybe we can use time to jump back and forth between those 2 axes if we don't have enough information in one column or the other. Oops. Back there. Okay, so we'll start with the initial velocity, and what we really have in front of us here are the x and y components of the initial velocity. Looking at the initial velocity is all in the x direction when we start. And so that means all the value will go into the x column. We don't have a component of initial velocity in the y direction, at least not initially. And then for final velocity, well, I really don't know anything about the final components of the final velocity, so I'm gonna skip that. Now I'll go to the acceleration. The only acceleration that we really have is due to gravity, and gravity is pointing down. That's in the y direction. Down is positive because of our choice of reference frame. So we have a positive 9.81. But what about the x direction? Well, it's at this point that some people say, well, there's going to be air resistance or drag, something like that, and in a real world situation, you would be correct. There's definitely going to be air resistance. It's definitely going to play a part in slowing down the object, but air resistance is an incredibly complex discussion. The book devotes about a page to the idea of air resistance, and it gives a couple of equations that can be used, but the idea behind air resistance is better suited for a classical mechanics course where we can utilize more advanced math like differential equations. And so we're going to exclude air resistance from our discussions in this class. I can only think of one instance where air resistance might come up as a part of a problem in chapter 8, but we'll address that when we get to it. But for now, no air resistance for this class, and so without having any air resistance, there won't be anything to speed us up or slow us down along the x-axis. As such, until further notice, we will assume zero acceleration along the x-axis. Now that should raise a flag because the definition of acceleration, regardless of what axes we're working with, the definition of acceleration is a change in velocity with respect to time. Well, we have zero acceleration, which means we're not changing our velocity. And so that means the velocity along the x direction has to be constant. If the velocity is constant, then the final velocity has to be the same as the initial velocity. And that means we know what this x component of the final velocity has to equal. It's 5. And you might be thinking to yourself, oh, good, now we have 3 pieces of information along the x column. We can put that information together and solve for the other 2 pieces of information, except that this is that one situation that doesn't work. If we try to plug that information into any of our kinematic equations, we will get undefined values for the displacement and the time. So if we can't use this combination of information, then how are we supposed to get values for delta x and delta t? Well, as we said, right here, we have to have the same times in each column. If I can solve for the time that it takes for this rock to fall along the y-axis, then I can use that in the x-axis to tell us how far the rock displaces from the base of the cliff. Well, that means I need one more piece of information in the y direction. So let's go back to our diagram here, see if we have anything else that we haven't picked up on. Remember that the displacement for the rock in the y-axis is 30 meters down. Down is the positive direction, and so we have positive 30 meters. And now we have 3 pieces of information in the y direction. We can use those to solve for the remaining 2 pieces of information. Now I'll just go ahead and go down the list here. We have given information in the form of initial velocity component, acceleration, and displacement. I want to solve for the final velocity component, which means there is no room left for time. Each kinematic equation can only incorporate 4 terms. So I go back to the list of kinematic equations and I look for the one that leaves out time. It's the last one. Now I'm only using information from the y-axis, and that means I'm only doing a one-dimensional kinematics problem. So I don't need the vector notation anymore. This is all in one direction, that is the y direction. And so I'm going to use this equation, but only with the information from the y column. Every value that I plug into this equation is going to come from the y column of our table. We're looking for the final velocity component. We need to take a square root of each side. Technically, we get a plus minus out of our root. Which one do we want? Well, our final velocity component should be pointing down, and down is the positive direction with respect to our reference frame, so we're going to go with the positive solution. We'll go ahead and plug all our values in. The initial velocity component was 0. 2. Acceleration is gravity, positive. Displacement is 30, positive. This is important with our root. We cannot have a negative quantity inside of that root. If you do, stop what you're doing, go back, check your work, see where the error is. But we're going to plug all of this into our calculator, and we're going to get the square root of approximately 589. And so the square root of that is 24.26. So it's at this point that I can now answer this question. What is the final velocity vector? I have the x and y components of that final velocity vector. We have an x component of positive 5, and so we denote that with I hat for the x direction, plus a y component of 24.26 j hat, signifies the y direction. Meters per second is the units. And now if I need to find the magnitude of that vector, magnitude mantra says square root of the sum of the squares. So we would square each of those components. And then we take a square root of that summation. Whoops, my calculator didn't like that. Alright, and I am getting a final velocity magnitude of 24.6. 0.76. So not that much more than the y component, but it is larger. And then the angle. The angle we can find by taking the inverse tangent of our y component over our x component. And that is giving me just a little bit over 78 degrees. So what does that mean for us? Well, as the rock, oops, let's zoom in here. As the rock hits the ground, it makes an angle with the ground, which is approximately 78 degrees. Moving on, so now that we have our final velocity taken care of, the only way that we're going to be able to solve anything else is we have to know the time of flight for this rock. So we'll come back to the information that we have in the y direction. We have our given information. We want the time. We don't really want to use any kind of calculated material unless we have no other choice. And so we need the equation from our kinematics that leaves out the final velocity. That's the second one. Again, we're only working with information in the y direction. And so I'm going to take that second equation and I will rewrite it so that it only applies to the y direction. You'll notice I dropped the arrow hats because everything that we're doing now is a one-dimensional kinematics problem. And the next step would be to rearrange the equation to solve for time. That's what we're trying to solve for. Right now, this equation is quadratic with respect to time. So go ahead and look through your values, see if there's anything that's helpful, and that initial velocity in the y direction is very helpful because it's 0. And if I plug in a 0 for that first term, well, now we don't have to go through any kind of setup with a quadratic solution. We can just rearrange things algebraically to solve for the time, and this would be root 2 delta y over a. We're only going to be working with positive time in this class. Go ahead and plug your values in. Delta y is 30. The acceleration is positive 9.8. Again, this is the importance of our reference frame and labeling things accordingly, because I need everything underneath this root to be positive. If it's not, go back and see where your error is. We need the square root of everything, which is going to come out to be approximately 3.5 seconds. So this rock will be in the air for 3.5 seconds until it gets to the ground. I'm going to go back and just double check my work here real quick. That didn't sound right. Nope, that's not. That is not 3.5. I thought that looked a little too big. It should be 2.47. Don't know why my calculator gave me 3.5, but we would have found that error when we check our work. But now that I know the time, I really don't have a choice when it comes to the x column of our table here. I need one more piece of information if I'm going to be able to solve anything else. So I will bring this calculated value over. Whatever time we get to move in the y direction is the time that we get to move in the x direction. And so now I will use that time in an equation to solve for delta x. But there's only room for 4 pieces of information in any given kinematic equation. Since these two are the same, I'm going to treat them as one value. And so I will use the acceleration, and at this point you really just have to flip a coin and decide, do you want to use the initial or the final velocity? And I'll just go with the final velocity. So what equation leaves out the initial velocity? That is the one right in the middle. And that equation, oops, move over a little bit. That equation says that delta x, remember we're working just in the x direction now, that equation is already set up to be solved for x, so I don't need to rearrange anything. I can just plug my values in from the x column. Delta x equals v final, which is 5 meters per second, times the time, 2.47 seconds, minus half of the acceleration times the time, but the acceleration is 0. So all that's left is that first term. So we need to take our time times 5, which is going to give us a displacement of 12.36 meters from the edge of the cliff. Okay, well, once our table is full, once we have all the terms accounted for, we can effectively answer any question that the book wants to throw at us in terms of the system. So back to the questions that we asked over here. What was the time of flight? Well, we got that, 2.47 seconds. What was the final velocity vector? Since I did not specify how I wanted that vector described, you're more than welcome to just provide the components of the vector. There's absolutely nothing wrong with labeling a vector using its component form, because as we know now, we can always take those components and convert them to magnitude and angle later on if we have to. And then the displacement, delta x, we found that right there. And let's see, there's one other question that I can pose to you. And I'm going to make some room over here. What I would like to know now is, what is the final displacement of the rock? And we know that displacement is the difference in the initial and the final values, which means right here, this is the final position of the rock. Right up here was the initial position of the rock. But we can also describe this as the combination of the changes in the x and the y directions. And we already know what those are. We know that we have a displacement of 12.36 in the I hat plus a displacement of 30 in the j hat, and now we're done. We've taken the values that we have for our displacement, we've put them together into the appropriate vector notation, and we're done. So now if I wanted to know the magnitude of that displacement, we would take the square root of the sum of the squares. 12.36 squared, 30 squared. Need a moment to plug all this into my calculator. And then we square root that. And I'm getting approximately 32.45 meters. Now, what does that final displacement vector look like? Going back to Chapter 3, we know that any resultant vector has to be drawn from the starting point to the ending point. So here's where things get a little bit different. I started right here. I ended right here. We have to draw our resultant vector from the start to the end point. That displacement vector, that is delta r. How well does that displacement vector describe the actual path of the ball? And the answer is not very well. And if I were to ask you to find the angle that our final displacement vector makes at the final position, well, that would be the inverse tangent of our y and x component of our displacement vector. So again, we need to plug all of this information into our calculator. We need an inverse tangent of 30 over 12.36. And this is only giving me 67.6 degrees. Well, our final velocity vector came in at 78 degrees. So why the difference? Well, the difference is because whenever we take vector components and we break them up or we put them back together, we're using trigonometry. When it comes to the kinematics and the true motion of the object as it moves through space, well, if you look at all of your kinematic equations, there's no trig in there. And so there comes a point in these problems where we have to know when is it okay to use the trig and when do we have to use the kinematics. And so here's how we're going to know that. I'm going to redraw this picture just because that one up there is getting kind of messy. So we have our x and y directions. We have the rock up on the cliff here, and the rock travels through this parabolic path. So this is the true motion of the ball. And everything that we have for the motion of the ball right there everything in here has to be described using the kinematics. So what we did by breaking everything up into the x and y components and carrying through with two one-dimensional problems, that's the kinematics. You'll notice that it was only at the very beginning of the problem and the very end of the problem where we actually considered breaking up the components or putting those components back together using the trig. So it's okay to use the trig here if you need to break your vectors up into components. And it's okay to use the trig down here if you need to take your components and put them back together. We're definitely using the components in the kinematics, but there's no trig. Okay, we use the trig to break up our vectors so that we can use those components in the kinematics. Then the kinematics tells us what the final values are going to be, and we can take those final components and use the trig to put them back together into magnitude and angle relationship. So if we were to try and use the trigonometry for the entire trip, well, that's where we would get a right triangle of components delta x and delta y. Oops, sorry, wrong axes. Delta x, delta y, delta r. And so this is why delta r does not describe the true path of our projectile. This is what we call our projectile motion. And so we have this projectile path, and it is parabolic. It is not a straight line like delta r would have us believe. Well, I think that's enough for today's video. So we've seen the importance of taking our two-dimensional vectors, breaking them up into the one-dimensional components. But once we do that, there's really nothing new, because we're just doing multiple one-dimensional kinematics problems, which we've technically mastered now that we're past the chapter 2 material. The only trick is that we have to be able to find enough given information in either column so that we can actually carry out a kinematic solution with one of those 5 equations. Then once we get the table filled in, we can recombine those vectors and answer any question that the book might pose to us. So in a couple of the future videos for this chapter, we'll see a couple more example problems with two-dimensional motion, and then we finish up the chapter with topics of circular motion and relative motion. So the next video, I think we'll devote purely to example problems with two-dimensional motion, like we saw here with the rock flying off the cliff. So see you at video part 2.